Okay, here is 6.3. We're going to continue our work with the unit circle, and from time to time I will refer back to the Ferris wheel problems that we did last week. Our essential question today is how can we define the values of sine for greater than 180 degrees? And it's called 6.3 more sine language. Okay, Clarita is helping Carlos calculate the height at different locations around the Ferris wheel. They have noticed when they use their formula, h of t is 30 plus 25 sine theta, their calculator gives them correct answers for the height even when the angle of rotation is greater than 90 degrees. They don't understand why, since right triangle trigonometry only defines the sine for acute angles. Carlos and Clarita are making notes of what they have observed about this new way of defining the sine that seems to be programmed into the calculator. Carlos says, for some angles, the calculator gives me positive values for the sine of the angle, and for some angles, it gives me negative values. Without using your calculator, list at least 5 angles of rotation for which the value of sine produced by the calculator should be positive. Okay, so we're talking about positive values of sine now. So I'd like to go up and look at, this is the closest unit circle that I can find, so I'll just go ahead and use this one. So I want to pretend for a second that I have an angle coming out like this. And remember, this is our reference angle for quadrant 1. And just to review reference angles real quick, like that's the reference angle for quadrant 2. That's the reference angle for 3. That's the reference angle for 4. Okay, so remember, you're looking at the angle it makes with the x-axis. So I have an angle formed here. And what if I told you that this was at 30 degrees? That means this angle is 30 degrees. This is 90, and this is 60. Okay, actually that's not the portion I want to be looking at here. I'm going to be looking here. 30, 60, and 90. Okay, so we know that this is a unit circle, so the hypotenuse is 1. And in a 30, 60, 90, we know that the short leg is half the hypotenuse. So the sine of 30 is 1/2, or 0.5 over 1. So the sine of 30 is positive 1/2. So it has a positive sine value because 1/2 is positive. So this, we learned the other day, would be the exact same thing. This is 30, 60, 90, and the relationship is still 1/2. Both of them have positive 1/2, but what is your angle of rotation? I'll do that in blue. So for this one, it was 30. For the next one, it was 90, 150. Oops, 150. Because the whole thing would be 180, and then this was subtracted, the 30 there. So what we're saying is that sine 30 and sine 150 should be the same. So just to quickly double check this, I would go to my calculator and I would erase these weird values, and sine 30, and then what if I go sine 150? Okay, so I'm not sure what happened up here. Hold on. Sine 30.5. There we go. So we can see how they're both equal to 1/2 in the calculator as well. All right, back to answering our questions. So let's see, 5 angles of rotation for which, so it would be anything between 0 and 180 really, right? Because anything in this region up here, when I do the opposite over hypotenuse, I'm always going to get a positive number, because the opposite is always going to be like this y value coming up, and the hypotenuse, that 1, is always positive. So you can list any numbers between 0 and 180. So I would say like 0 degrees, Without using a calculator, list at least 5 angles of rotation for which the value of sine produced should be negative. So going back to my picture, which is a little jumbled up right now. So here's our negative ones. Whoa. So let's say I had, I'll use red so you can see it better. Let's say I had, they'll just use the one they have for us here, okay? So this, the angle, the reference angle is 45 degrees. Okay, actually I don't want to use 45 degrees. I could, but I don't want this to go too long because this is review, and that would take me a little bit longer. So we'll just stay with our examples from before. So remember I have 1/2 and 1, but this time it's negative 1/2. Because think about the coordinates of this here, right? I would have to go 1/2 down. So the sine of 30 this time, which is really the sine of what? Well, here's 180 degrees, and then another 30. So this is like the sine of 210 is going to be equal to, this time it's negative 1/2 because I'm going down 1/2. So negative 1/2 over 1, which is just negative 1/2. So the sine of 210 equals negative 1/2. And just to prove that, that's not what I needed. I would go sine of negative 0.5. That's not what I needed. Oh no, I'm sorry. Sine of 210 should be negative 0.5. Yeah, there we go. So sine of 210, and that's why it's negative 0.5. So you can see how it would be the same thing if I would come over to this quadrant here. This would always be, the opposite would always be negative, and the hypotenuse is always positive. So in this case, it's everything from 180 to 360, 181, 211, 212, 302, and 359. Okay. Yeah, says Clarita. Sometimes we can even draw a triangle at certain positions on the Ferris wheel, but the calculator still gives us values for sine at those angles of rotation. List possible angles of rotation that Clarita is talking about. These are positions for which you can't draw a reference triangle. And then, without using your calculator, give the value of the sine that the calculator should provide at these positions. Okay, so for number 3, where can't we draw a triangle? Well, we can't draw, we can't draw a triangle when we go here, 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 and here. Because when I go out here, I have a reference angle, right? When I come down to here, it's just a line. It's just a line. It's just a line. And it's just a line. So those are the positions, but it's still surprisingly enough has a sine value. So I like to start thinking about what those points are. So this is the point 1, 0. This is the point 0, 1. This is the point negative 1, 0. And this is the point 0, negative 1. So I start thinking about these values, and I start thinking about what sine is. And what sine is, if you remember from the last one, like when I had this, I had 1/2, when this was 30, right? And then this was 1, and I found out that sine 30 was 1/2, because 1/2 over 1 is 1/2. So do you see how sine is actually always, you could think of it as just always the opposite, okay? And what is the opposite? Well, the opposite is always the y value of the point. Like this point right here is the point 1 and then 1/2. And this was my sine value because when I divide by 1, it doesn't do anything to the number, since the radius is always 1. So it's safe to say that the sine is actually just equal, if I want to simplify things, it's just equal to the y value. Okay, so all I have to do is look at what the y value is in each of these odd positions. So the sine of 0, which is just a line coming out like this, is that y value. The sine of 90 is that y value. The sine of 180 is that y value. The sine of 270 would be this y value. So it's just the y coordinate. So let's go ahead and write that out. So again, those are 0, 90, 180, 270, and 360. So the sine of 0 is 0, because remember, what's the y value at that 0? It's 0, okay? 90, again, is 1. Okay, sine 180 was, what's the y value at 180? It's 0. Sine 270, what's the y value? Negative 1. That's 270. And sine 360 is back to 0. Carlos. And because the symmetry of the circle, some angles of rotation should have the same values for sine. I'll read that again. And because of the symmetry of the circle, some angles of rotation should have the same values for sine. Without using your calculator, list at least 5 pairs of angles that should have the same sine value. Okay, so this is what I talked about in the very, very, very beginning. So remember we went out like this, and we talked about how this was 30, and how that was 1/2, and we talked about how this was 30, and this was 1/2. So remember we said that sine 30 was 1/2, but then we also said that this one had the same value. So this, remember, this angle, which we determined as sine 150, also was 1/2. So there's a pair right there. We have 30 and 150. And then you can come up with other ones probably on your own. I'll just do one more. So let's say I come out like this, and we say that that's 70 degrees. So if I were to come out like this and make this 70 degrees, I would have sine of 70, and then sine of, what's that one? Well, I would come here to here. So what is that whole spot? It'd be 180 minus 70. So sine of 110. Okay, so you can write those two down and then come up with 3 more on your own. Sine 70, sine 110, sine 30, and then sine 150. So we're just coming up with matching ones there. I'll plug in my Apple Pencil real quick. Okay, right, says Clarita. And if we go around the circle more than once, the calculator still gives us values for the sine of the angle of rotation. And multiple angles have the same value of sine without using your calculator. List at least 5 sets of angles of rotation, while the calculator should produce the same value of sine. Okay, so for 5, we're talking about the ones that go around the circle multiple times. So keep referring back to the circle here. What we're talking about here is, okay, if we have our 30, what if we go around the circle again? Okay, so what if I go 90, 180, 270, 360, and then to here? Do you see how that's the same angle? So that would be 360 degrees to here, and then another 30. So that would be sine 30 should be equal to sine 390. Okay, so you just got to come up with 4 more of those. Okay, so what if I just went out like 1 degree? Okay, what if I just went out sine of 1 would equal the sine of 361, because I would go around and then up 1 degree. It'd give me the same thing. Or I could go around twice. Okay, you could go here, here, and here, and then it would be up in the 700s. Okay. All right, so just write down 5 of those that would be the same. So we said sine 30 equals sine 390, and then we also said that the sine of 1 is equal to the sine of 361. Carlos, so how big can the angle of rotation be and have the same sine value? How small can it be to have the same sine value? Well, we could go around the circle an infinite number of times, right? So it could be infinity degrees, and you can just keep getting the same ones as long as you keep going perfect circles around and ending up in the same spot. It's really not going to change. Now, the how small question is kind of interesting, and we haven't talked a ton about this, but how small starts to get into negative numbers. So let's say, for example, we draw our 30. Okay, so I have my sine of 30. Now, instead of spinning counterclockwise, let's say that I spun clockwise, and I went here to here. So what would that be? Well, when I'm going in the clockwise direction, it actually counts negative. So if I want my angle to go positive, again, I would go in the counterclockwise direction. If I want my angle to go negative, I would go in the clockwise direction. So on this one, I went a negative distance because I went clockwise, and I went a negative 330 because I went a full circle, everything except this. So sine 30 is equal to sine negative 330. And to prove it to you, I'm just going to go sine, well, we all know sine of 30 is 0.5. I don't need to enter that yet again. But if I go the sine of negative 330, I also get the same thing, which is 0.5. So come up with a few of those on your own. That would be equal. Oh, no, actually. Let's see. Oh, it says this one was just how big and how small, right? So it could be anything. This is just, it'd be negative infinity. This just be negative infinity to infinity. How would you answer Carlos and Clarita's questions? That kind of went into this, actually. While we're asking these questions, Carlos says, I'm wondering how big or how small the value of sine angles can be as the rotation gets larger and larger. We talked about that. Okay. Without using the calculator, how would you answer Carlos's question? Oh, we're talking about the sine values on 7. And this is the intro to it. So we're not talking about the angle of rotation now, but we're talking about when we do those really big angles of rotation, what's the biggest sine could be? And what they mean by that is like when I did sine 30, what did I get? I got a half. And when I did sine negative 330, what was my result? My result was 1/2. Okay, if I did sine 390, what did I get? I got a half. So the question here is, what's the biggest or smallest thing that you can get here? Well, if the hypotenuse is always 1, okay, if the hypotenuse, just like that's why I put this picture in here, actually one of the reasons. If the hypotenuse is always 1, and it is the hypotenuse, it doesn't matter how many times I spin it around, okay? It's not going to change the opposite over hypotenuse relationship. And this always has to be smaller because it's not the hypotenuse. So I'm always going to get something that is less than 1 or greater than negative 1 for those sine values there. So, so for 7, I would just say the value of sine is in between negative 1 and 1. Okay, sine is between negative 1 and 1, because the opposite can never be bigger than the hypotenuse. Okay, so I'm going to use this picture again for this one, I think. All right. Clarita. No, we talked about that. Okay. Cool. Well, I think that's going to take us through part 1, and I'm going to stop the video here and do a separate video for part 2, but hopefully that was helpful.